can machines think? I mean, it's one of those questions, isn't it?
Right.
Feels ancient, but also, like, incredibly now. Where did it really kick off? And how did one specific thinker just completely flip the script on how we even approach it?
We're going straight to the source on this one. We're talking Alan M. Turing and his foundational 1950 paper, Computing Machinery and Intelligence.
That's the one. And that paper, that's your source material for this deep dive.
Yeah.
The mission today. Get right into Turing's thinking, how he sidestepped the whole messy definition of thinking and machine, and his surprisingly bold take on what computers could ultimately do. We want to cut through all the later interpretations and just see what he said.
Yeah, it's a fascinating paper. It really did set the stage. And you read it now, and his core questions, his approach, they still feel incredibly relevant.
Yeah. Okay, let's dive in. So Turing starts with the big one. Can machines think? But almost straight away, he says, hang on, defining machine and think, based on how people normally use the words, that's not going to work. He even calls trying to settle it with something like a Gallup poll absurd.
Right, because language is just too slippery, isn't it?
Yeah.
What does think really mean day to day? You just argue forever. He needed something concrete, something testable.
And his solution was, well, it was clever. He basically says, let's swap that fuzzy question for a different one, a game. He calls it the imitation game.
Yeah, and the setup is deceptively simple. 3 players, a man, let's call him A, woman, B, and an interrogator, C. Crucially, they're all in separate rooms.
Separate rooms. Okay, how do they talk?
Through a teleprinter. So basically type messages. No voice, no handwriting, nothing visual.
Ah, so it strips away all the physical stuff.
Exactly. The interrogator
Yeah.
just sees messages from X and Y and has to figure out which one is the man and which one is the woman.
Okay, so what are A and B trying to do?
Well, C wants to get it right. Player A, the man, is actively trying to fool C into thinking he's the woman. Player B, the woman, is trying to help C figure it out, presumably by just being herself, answering truthfully.
So A is imitating, B is helping. What kind of questions get asked?
Anything, really. Turing gives examples like, tell me about your hair. Player A, the man trying to sound like a woman, might say, oh, it's shingled, about 9 inches. The woman would give a straightforward answer. Or they might be asked to write a poem or solve an arithmetic problem, maybe even discuss a chess move. The point isn't always technical accuracy for A.
It's about the imitation.
Exactly. Turing even suggests the machine, later on, might deliberately get a math question wrong to seem more human, less like a perfect calculator.
So it's about conversational mimicry, and this is where the machine comes in, right?
Sure.
Turing's big replacement question is, what happens if a machine takes on the role of player A? If the machine tries to convince C it's human, will C get it wrong just as often as when A was a man trying to imitate a woman?
That's it. That game, that test, that is Turing's working definition of thinking for this paper.
And why is that such a big deal?
Because, well, it completely bypasses all those thorny philosophical debates about what consciousness is or what thought feels like inside. It shifts the whole focus onto observable behavior. Can the machine act like it's thinking in this specific conversational context? If yes, then for the purpose of the game, it passes. It's pragmatic.
Okay, so he sets up the game. Then he asks, is this game even, like, a useful question to chase? He argues yes, because the alternative, defining thinking directly, just goes around in circles.
And the game's design, using that teleprinter, is smart. It levels the playing field. The machine isn't judged on whether it looks human or can run fast. The human isn't judged on physical strength. It's purely about intellectual performance through language.
Right. So the test is set. Now, the other tricky word, machine, he has to define that too, doesn't he? He mentions all sorts of engineering possibilities, but says the real interest, the thing driving the thinking machine's idea back then, was something specific.
Yes. He puts a restriction on it for the game. The only kind of machine allowed to play the part of A is a digital computer.
Okay, but isn't that like a really narrow definition? Isn't he potentially ruling out other ways machines might think?
He addresses that. He argues it's not too drastic, mainly because he believes these digital computers have huge potential. He thinks they can eventually do well in the game. He's not saying the computers they had then, in 1950, could pass, but he's asking, are there imaginable digital computers that could? It's about the future potential of this class of machine.
So when he says digital computer, what's he actually picturing?
He describes them functionally. They're machines designed to do anything a human computer could do following fixed rules. Imagine someone meticulously doing calculations with paper, pen, and a big book of instructions.
Okay, like step by step.
Exactly. And he breaks the digital computer down into analogous parts. There's the store, which is like the human's paper or memory. It holds the data and instructions. Then the executive unit, which does the individual steps, add this, multiply that, write down to zero. And finally, the control, which makes sure the instructions, the table of instructions, are followed in the right order.
And these instructions are like commands. He gives an example, something like, add number in location X to number in location Y, store the result in Y.
Pretty much. Though inside the machine, it's not English, it's coded, probably numbers representing locations and operations. Normally, it just steps through them one by one.
But then he mentions something crucial, conditional instructions.
Yes, the if-then kind of instruction. Like if the number in storage location 123 is 0, then jump to instruction 500 next. Otherwise, just carry on to the next one.
And why are those so important?
Because they let the machine adapt its behavior based on results. It can repeat loops, make decisions. It doesn't just follow a single linear path. Turing uses that analogy of a mother telling her son Tommy to check the cobbler every day versus just putting up a notice. The notice, like a conditional instruction, provides a standing order that governs behavior based on circumstances.
Got it. So these machines can precisely mimic a human following rules. And programming is just translating those rules into the machine's instruction code.
Right. He also mentions you could add randomness, like a virtual dice roll, or think about theoretical machines with infinite memory. And he makes a really interesting historical point about Charles Babbage's analytical engine from way back in the 1800s.
Babbage, the mechanical computer guy.
Yeah. Turing points out that Babbage's mechanical engine already had the core ideas. Store, executive, he called it the mill, control, instructions.
So the fact that modern computers were electrical wasn't the fundamentally important thing. People were maybe getting hung up on that, comparing it to nerves.
Exactly. Turing calls that a superstition. Since Babbage's mechanical engine could theoretically do what digital computers do, the electricity wasn't the defining feature. The mathematical function, what it computes, that's the key similarity. All these machines are functionally equivalent in a deep way.
Okay, so we have the test the imitation game, we have the player, the digital computer, defined by its store, executive, control, and crucially, those conditional instructions. Now, what's their ultimate capability?
Right. He classifies digital computers as discrete state machines. They move in sudden jumps between clearly defined states. Think on-off, not like a dimmer switch that slides smoothly.
Unlike, say, a slide rule.
Exactly. And the big thing about these discrete state machines, predictability. If you know its state right now and the input it gets, you know exactly what state it will be in next. Unlike, say, the weather, where tiny changes can have huge effects down the line.
Even though the number of states is massive, he mentioned some crazy number for the Manchester machine.
Yeah, like 10 to the power of 50,000. Huge. But still, in principle, deterministic state to state. Storage capacity is the practical limit, like how much paper the human computer has.
Okay, but here comes the really mind-bending part, right? Universality.
This is the core of his argument about potential. Turing explains that any digital computer, as long as it has enough memory, store, and runs fast enough, can be programmed to imitate any other discrete state machine.
Wait, any other one? So you don't need a special machine for weather simulation and another one for chess?
Nope. One sufficiently powerful universal digital computer can become the weather simulator, or the chess player, or the text processor, just by loading the right program, the right table of instructions. This makes all these computers, in a theoretical sense, equivalent.
Wow, so how does that connect back to the imitation game?
Because of universality, the question, can any imaginable digital computer pass the test, boils down to, can one specific universal digital computer, if we give it enough memory, speed, and the right program, pass the test? And that is where Turing pins the maximum potential. The limit isn't the specific hardware design, it's the universal ability to simulate any discrete process. And crucially, he assumes that the kind of thinking needed to pass his game can be represented as such a discrete process. Therefore, the potential ceiling includes passing the test.
So he's basically redefined thinking as passing the game, defined the machine as a universal digital computer, and argued its theoretical potential covers passing that game. He genuinely believed it was possible.
He did. He even made a prediction. He thought around the year 2000, give or take, computers with about 1 billion bits of memory, which was way more than they had in 1950, could be programmed well enough that an average interrogator playing the game for 5 minutes would only have a 70% chance of guessing right. He also thought people would just start talking about thinking machines without raising eyebrows.
Bold predictions. But he knew people would object, right? He spends a lot of time tackling counter-arguments.
Oh yeah, 9 of them. He really tries to anticipate the pushback.
Let's hit a few key ones. What about the theological objection? Machines don't have souls, only humans do.
Turing basically finds this unconvincing. He questions whether it limits God's power. Why couldn't God give a machine a soul? He kind of compares it to old arguments against science based on religion, like Galileo facing objections about the Earth moving. He suggests these arguments don't tend to age well.
Okay, then there's the heads in the sand view, basically. I don't like the idea of thinking machines. It's scary. Humans must be superior.
He acknowledges it's a common feeling, especially for intellectuals who pride themselves on thinking.
Mm.
But he says it's not really an argument, just wishful thinking based on wanting humans to stay on top. He kind of wryly suggests maybe consolation is needed, not refutation.
What about the mathematical objection? This one seems more technical. It uses things like Gödel's theorem, even Turing's own work on uncomputable problems, to say there are definite limits to what any formal system or machine can prove or decide. Humans don't seem limited like that, do they?
This is a subtle one. Turing's response is, well, how do we know humans aren't subject to similar limitations? Maybe we just don't notice our own boundaries.
Right.
That feeling of superiority when a machine hits a wall defined by logic might be illusory. He even floats the idea of a hierarchy of intelligence, machines potentially surpassing humans.
Okay, then the big one, the argument from consciousness. Professor Jefferson's point that a machine can write a sonnet, perhaps, but it can't feel it, it doesn't know it wrote it, it can't experience emotion.
Turing admits this feels like the strongest objection. But he argues if you push it to its extreme, it becomes solipsism, the idea that you can only be sure of your own consciousness. Since we don't usually operate like that, we assume others think and feel based on their actions and words. The polite convention, he calls it. So he argues, someone holding this view should probably accept his imitation game as a practical test, rather than demand impossible proof of inner experience. He thinks a machine could give sophisticated, non-obvious answers about poetry or feelings in the game. Solving the mystery of consciousness itself isn't needed to answer his question about the game.
And the catch-all arguments from various disabilities. Machines can't X, Y, Z, can't be kind, have humor, fall in love, enjoy strawberries, make mistakes, think about themselves.
He thinks many of these are based on just looking at the simple machines they had then, especially ones with tiny memories. He argues machines can make errors of conclusion, logical mistakes, not just hardware failures. He thinks they can process their own programs, effectively thinking about themselves. Things like enjoying strawberries seem irrelevant to the game, but underlying abilities like friendliness might be programmable. He feels many boil down to the consciousness argument, again, an unease with the idea of mechanical processes producing these behaviors.
And Lady Lovelace's objection, that machines only follow orders, they can't originate anything truly new, based on Babbage's work.
Turing pushes back hard here. He quotes others who disagreed even about Babbage's engine, and he points out that universality means one machine can behave like any other. As for originality, he says machines surprise him all the time, mostly because he can't foresee all the consequences of complex programs. He argues that maybe nothing is truly new anyway, or that surprise is more about our own limitations. And crucially, he links this to a learning machine could certainly produce unexpected, seemingly original output.
He also bats away arguments about the brain being continuous versus discrete machines, about human behavior being too informal for rules, and even ESP, briefly.
Yeah, he really tries to cover the bases, often bringing it back to, does this objection actually prevent a machine from passing the test? That's his focus, the behavioral outcome.
Okay, so he's argued it's possible, dealt with objections. How did he think we should actually do it? What's the path forward? He said the main problem wasn't hardware, but programming.
Exactly. He thought the memory required, maybe a billion bits, was achievable and speed wasn't the bottleneck. The massive challenge was figuring out the program that would produce intelligent game-passing behavior.
And his big idea for that, instead of trying to program an adult mind from scratch with all its complexity.
You simulate a child's mind and then you educate it.
A child's mind, why?
He reasoned it might be simpler initially. Less built-in complex behavior, maybe more like blank sheets or raw potential in the store. Easier to program the starting point, perhaps. Then the real work becomes the education process, teaching this child machine how to interact, learn, and eventually play the game.
And he uses an analogy for this learning process, evolution.
Yeah, it's quite striking. The initial program of the child machine is like the genetic inheritance. Changes made during its education may be random tweaks or guided adjustments or like mutations. And the judgment of the programmer, deciding if a change makes the machine better at the game, acts like natural selection.
But hopefully faster than actual evolution because the programmer is guiding it intelligently.
That was the hope. He talked about needing sophisticated teaching methods, probably involving language, maybe like how Helen Keller was taught despite lacking sight and hearing, not just simple rewards and punishments.
He even suggested building in basic logic systems so the machine could understand commands by reasoning from stored facts, like teacher says do homework, teacher is reliable, therefore I should do homework.
And he made a distinction. The rules that change during learning aren't the machine's fundamental operating rules, those are fixed, like physics, but higher-level ephemeral rules, like laws that can be amended.
And one really interesting consequence he foresaw: if you successfully educate a machine this way.
The teacher, the programmer, might actually lose track of exactly how it works internally. It becomes too complex to hold a clear picture of, unlike a simple traditional program.
He also had that interesting point about intelligent behavior not being perfectly rigid.
Right. Not random, but a slight departure from totally predictable, disciplined computation. Enough flexibility to avoid getting stuck in loops or making obvious errors, but not perfectly by the book all the time. Learning, he thought, would naturally introduce this kind of useful fallibility.
And maybe a bit of randomness helps in the learning process itself, like searching for solutions.
He thought so. Useful for exploring possibilities, like finding a needle in a haystack, or like evolution trying out variations.
So what was the first step then? Teach it chess or teach it English like a baby?
He wasn't sure. He basically said, look, both abstract games and trying to build up from sensory input and language like a child. Both approaches seem worth trying. We should explore them.
Okay, so let's pull this all together. We've dug into Turing's paper, his clever reframing of can machines think, into the imitation game, his focus on the digital computer as the candidate machine, the powerful idea of universality showing its immense potential, how he tackled objections by always coming back to the behavioral test, and finally, his vision for achieving artificial intelligence not by direct programming of an adult, but by creating and educating a child machine, almost like guided evolution.
And we shouldn't forget his 1950 prediction. Give it 50 years, enough memory, the right programming approach, and machines could plausibly pass his test, fooling humans a good chunk of the time.
It's just incredible how much of what he laid out then still shapes the conversation today, isn't it? He gave us a concrete benchmark, maybe imperfect, but concrete, and a really expansive view of what computation might achieve.
Absolutely. And maybe a final thought for you, drawing from Turing himself. He noted that intelligent behavior seems to involve that slight departure from perfectly rigid, rule-bound computation. It avoids pure randomness, but also isn't just clockwork logic. What does that subtle balance tell us about intelligence itself, whether it's ours or artificial? Something to ponder.